Good evening, everyone. Good evening. We'll wait for a few more minutes, couple more minutes maybe. People are still joining. Okay. I'm audible, right?
Yes, sir.
Okay, good. Good evening, everyone. My name is Amit. Let me share my screen first. Yeah, is my screen visible? Are you able to see my screen?
Yes, sir.
Okay, good. Good evening. My name is Amit. This is week 8 for Gate Physics Solutions hosted by NPTEL. Um, I am taking the electronics section, and last week we had discussed, we had begun digital electronics. This week also we'll continue digital electronics, solve some circuits related to gates and their algebraic expressions. And next week we'll continue with digital electronics. Next week will most likely be flip flops, counters, and ADCs and DACs, that's digital to analog converters and analog to digital converters. So I'll begin. We had talked about this last week that Boolean algebra is essentially we play about with the values of 0 and 1. That's what our focus is, because we are primarily interested in binary. So this is the one, and the three primary so to say functions are conjunction, disjunction, and negation. So we know that, and finally we had the two basic laws, the De Morgan's laws, which have been listed here. So AB dot denotes and. So AB whole bar is nothing but A bar. Bar means negation plus B bar. And the second De Morgan's laws is A plus B whole bar. Now plus denotes OR gate. A plus B whole bar can be written as A bar dot B bar. These are the two very uh, these are arguably the most two common properties that we encounter using solving Boolean algebra. And these are just a list of the truth tables of the gates that we typically encounter. The simplest, of course, is the one input NOT gate, and then we typically encounter AND gate and OR gate. However, NAND and NOR are what we saw in the last session, that these are called the universal gates. Why they are universal? Because every other logic can be schematic can be made, and in reality a circuit can be designed just by using NAND gates or NOR gates. This functionality is not there for any other gate. So only using NAND and NOR you can design an entire circuit, however complex it may be. Right. So we went through some questions in the last class, and so now I'm going to be playing a video, and just let me know if you're able to hear the audio or not. Okay, is it clear?
Yes, sir.
Okay, I'll start playing the video now. The problem statement. Is it audible?
Yes, sir.
Okay, I'll continue playing the video. Please stop me. Your voice is audible to me. Please stop anywhere. I have my paper and pen ready. I'll be able to address any of your doubts in any of the questions at any point of the time. Okay, I'm playing the video now. The problem statement from GATE Physics 2021 reads as follows. The above combination of logic gates represents the operation. We have been given a circuit which is using three logic gates, and we are required to find what does the output represent. The four options are OR gate, AND gate, NAND gate, or NOR gate. This is a multiple choice question with only one correct option, and we need to find the correct option. This is a table depicting the logic gates. So this is the name of the logic gate on your first row, and then we have the algebraic expression. For instance, NOT gate can be represented where the A is the input to the signal, and this bar denotes that this is the expression for the NOT gate. Similarly, AND gate can be as A times B. OR gate is A plus B, and these are the symbols for them. So NOT gate has a right pointing triangle with a circle at the vertex of the triangle. A is input and X is the output. Similarly, AND gate, it's a two input AND gate. So we have A and B are the inputs and X is the output. So for OR gate, A and B are the inputs and again X is the output. And there are other gates that have been demonstrated here. NAND gate is nothing but not AND gate followed by a NOT gate. So the symbol would be this symbol for AND gate followed by the circle at the vertex which depicts a NOT gate. Similarly for NOR gate, and similarly we have XOR and XNOR. So finally we have the truth tables for them. The truth table, what essentially is this mean? It lists all the possible combinations. So for instance, when there is only one input, it can be either true or false. And then based on these sets of input, we try to obtain the outputs. So for instance, in NOT gate, if there are only two possible combinations, the input is low and the input is high. So we've listed them. Now what a NOT gate does is simply an inverter. So it inverts whatever the input is being provided. So if the input is 0, the output would be 1. And the input is 1, the output would be 0. Similarly, in case of AND gate, what happens? This is a two input AND gate. So we are providing two inputs B and A, and the four possible combinations are both the inputs are 0, only A is 1, B is 0. The third possible combination is B is 1, A is 0, and the fourth possible combination is A is 1 and A is 1 and B is 1. These are the only four combinations possible with a two input NAND gate. So based on these inputs, we try to find the output. Now note that X is A times B. So 0 into 0 is 0. 0 into 1 is 0. 1 into 0 is 0. And 1 into 1 is 1. So this table, which contains all the possible combinations of inputs and corresponding outputs, is known as truth table. And in this specific case, this is a truth table for an AND gate. Similarly, using this algebraic expressions, we can obtain the truth table for all the gates listed here. And for that matter, we can obtain a truth tables for every combination circuit. In our question, we are given this circuit. So let's assume that the inputs are A, the top input is A, the bottom input is B, and let's say that the output we want is Y. So output is Y. Now let's just first look at the top gate, which is depicted in this blue rectangle here. Note that this is a NOT gate. Yeah, Rituraj, you were saying something?
NAND gate,
Oh,
whole combination.
you are saying the answer. Okay, okay. Yeah, you're correct. But let's go ahead and because sometimes what happens is that the process is also important. It's a very simple question. I get that. You can solve it orally, which you just did. That's very good. But for the sake of completion, we'll go ahead with this. Okay, so just bear with me. And we know that for NOT gate, the output is just the input inverted. So I can write that the value of this node would be nothing but a bar. Why a bar? Because a is the input to this NOT gate, and this NOT gate will simply invert it and be depicted algebraically using the expression a bar. Similarly, if you look at the bottom rectangle in orange here, so the input to this bottom rectangle is B, and this is a NOT gate. So what will be the output of this NOT gate? The output of this NOT gate will simply be B bar, because B is the input to this NOT gate or this inverter. Now let's look at this green rectangle. This green rectangle is nothing but an OR gate. OR gate, and we know that the output of an OR gate, the algebraic expression, if you see from the previous slide, it is just the summation of two inputs. So let's write plus in between. That depicts that this is an OR gate. And on the left side, we have the first input. The first input to this OR gate is nothing but A bar. This is the first input to this OR gate. The second input to this OR gate is nothing but B bar. The second input is B bar, right? So what I get, Y is equal to A bar plus B bar. Now, there's something called a De Morgan's theorem. Or De Morgan's laws, whatever you may prefer. So it says that AB whole bar is equal to A bar plus B bar. There are actually two of them, two laws. Second says that A plus B whole bar equal to A bar times B bar. So we notice that the output here we have obtained is A bar plus B bar. And we know that using this first De Morgan's law, we can write A bar plus B bar as nothing but AB whole bar. Now please note that this is nothing but the algebraic expression for a NAND gate. So note that the expression we came about is AB whole bar. And if you go back to our previous slide here, we know that AB whole bar. So this is A, this is B, this is the output X. So we know that the output X can be written as AB whole bar, and this is the expression for a NAND gate. And we have obtained that AB, the output for this circuit is AB whole bar. Hence we can call this output, this whole circuit can be represented just by a simple NAND gate. Okay, so the answer here would be B NAND, because we obtained that if the inputs are A and B and the output we obtained was AB whole bar, which is the algebraic expression for a NAND gate. So the correct option here is B. Okay, any comments, any questions regarding this question? Rituraj solved it for all of us. Anything? Okay, so we'll move forward for the next question. The problem statement from Gate Physics 2016 reads as follows. For the digital circuit given below,
sir,
the output
screen
X...
is not visible.
Sorry?
Screen is not visible.
Oh, sorry. My bad. Wait. Okay, my PowerPoint somehow got disconnected. It's visible now?
Yes, sir.
Okay. From Gate Physics 2016 reads as follows. For the digital circuit given below, the output X is... We have been given a circuit with three logic gates, and we are required to find the output X, which is on the right side. The three inputs are A, B, and C, and we have been given four options. This is a multiple choice question with only one correct option, and we have to choose the correct option. This slide shows the gate. These are two input logic gates. So and there's nothing but we list. I am skipping this part because we just went through. So here what I'm doing is I'm explaining that this is the name of the logic gate. This is the expression, and this is the truth table. We just saw that, we talked about this in the last question. So I'll just, for the interest of time, I'll skip this so that we get to the question directly. Obtained for each of these logic gates, and for that matter for each even complex combinatorial circuits. This was the problem that was given to us. So we had a NOT gate at the top, we have an OR gate at the bottom, and we have a NAND gate at the right. I've identified these gates because you see these here. So just based on how do they look like, we can identify them, right? So now let's just first look at the top NOT gate. So if you look closely at this NOT gate, the input to this NOT gate is A. And we know that the expression, the output expression for the NOT gate is nothing but the inversion of whatever is being provided to it. So you can see that in this case. So for NOT gate, the output is nothing but, this is the output. So output is nothing but input, the bar of input. So if I see it here, so the output would be nothing but the bar of input. The input is A to this NOT gate. So the output would be A bar. Similarly, now if you look at in the orange rectangle, you see an OR gate. This is an OR gate. So what does OR gate do? OR gate sums. So the output here would be the sum of the two inputs. So the two inputs are B. So I'll write plus symbol here first, and the two inputs are B and C, right? So the output for this OR gate would be B plus C, correct? Now finally look at this green rectangle. So the green rectangle is nothing but a NAND gate, right? And what is the output of a NAND gate? The output of a NAND gate is, let's say, whatever the input you are providing here, and let's call this input P, and let's call this input Q. So the output X for this NAND gate would be P times Q, and then a whole bar of it. P times Q whole bar. This is what the algebraic expression for a NAND gate looks like. Now note that P is equal to A bar. P is nothing but, this is a wire here. So the value of P, so we know that, now we know that P equal to A bar. And we also know that, look at Q. Q is nothing but the output of this OR gate here, which is B plus C. So I can write and Q equal to B plus C. So let's put both these values in this expression. So then X would become P. P is nothing but A bar. Note that P is nothing but A bar times, this dot denotes a multiply, times Q. Q is nothing but B plus C. And then finally we have this whole bar. So this is what it comes out to. Now this is what we have obtained, that for this complete circuit, which has inputs A, B and C and these three logic gates, the output X we have obtained in terms of the inputs A, B and C, and the output X is related to A, B and C using this expression. Now coming back to the question, what we had obtained was that X is equal to A bar times B plus C whole bar. So X was A bar times B plus C whole bar. This is the expression for X. And we know that, so option B matches it exactly. So you know that's A bar dot B plus C whole bar, right? So option B is the correct one. Yeah. Any doubts, any comments regarding this? What we did in this question is the very similar thing that we did earlier, right? So here what I have done was, my screen is visible, right?
Yes, sir.
Okay, so what I did is the same as the previous question that we had talked about. We just put the inputs and we just put the inputs and we try to solve the expression. That's all. I said nothing fancy. So this is A bar, which I told you. So you saw the expression, A bar B plus C, and then we followed the same process flow that we followed the last time. It's very simple, very straightforward. I'm just explaining it step by step so that this process gets ingrained in your minds, and however complex the circuit is, you'll be able to handle it. The beauty of digital electronics is it's very simple. There are just two formula, that's De Morgan's laws, and four laws. 0 into 0 is 0, 0 into 1 is 0, 1 into 0 is 0, 1 into 1 is 1, and similarly for the OR. So that's the only thing you have to remember, and you can solve every complex, however complex the circuit is. And we'll solve some complex circuits today itself, right? So now let's start with the next question. I'll play the video now. Okay. The problem statement from GATE Physics 2015 paper reads as follows: which one of the following does not represent an exclusive OR operation for inputs A and B? So this means there are two inputs given, A and B, and we need to find that which one of these following does not represent an XOR operation. So these are the four options. This is a multiple choice question with only one correct answer, and we need to find the correct one. Now, this is the symbol of an XOR logic gate. This is how it's represented. The two inputs are A and B, and the output here we can see is Y. And this is the symbol for that, and it is represented using this. So plus, and the plus is encircled in a circle. So, and algebraically this is represented as this: A bar B plus AB bar. A dot is nothing but multiplication, and bar is your negation, right? And this is the truth table for this XOR symbol. So this is a two input one. So the truth table is nothing but we list all the possible combinations that are there, and then we try to find the output. So for instance, since it's two input, the possible combinations are A is 0, B is 0. Second combination is A is 0, B is 1. Third possible combination is A is 1, B is 0. And the fourth and last combination is A is 1 and B is 1. Now we'll try to evaluate the output value for the first row. So when input A is 0 and B is 0, we'll try to evaluate what is the value of Y. So note that the expression for this is A bar B plus AB bar. So let's say for the first row, A is 0, B is 0. So A is 0, so 0 bar will 1. 1 times 0 is 0 plus 0 times 1. So answer will come out to be 0. Second, when A is 0, B is 1. So A is 0, the first term will come out. I'll do the first row, okay, since I didn't do it here properly. So we know that the A is 0 and B is 0. So we'll say 0 bar dot B is 0, 0 plus AB bar. The value of A is 0 and B is also 0, 0 bar. So this will come out to be 1 times 0 plus 0 times 1, which is 0 plus 0. 0 plus 0 is 0, and hence it will be 0. Now I will go to the second row, okay. So this is the first row I just did it. To be 0 bar times 1 plus, now we are looking at the second row, 0 times 1 bar. So that will be 1 times 1 plus 0 times 0. So it will come out to be 1, and we know this comes out to be 1. Third, A is 1, B is 0. So let's put this here. So it's 1 bar times 0 plus 1 times 0 bar. So that comes out to be 0 times 0 plus 1 times 1, which is equal to 1, and hence the answer is 1. The fourth is both are 1. So we'll try to put that here. 1 bar times 1 plus 1 times 1 bar. This will come out to be 0 times 1 plus 1 times 0. So this comes out to be 0, and this also comes out to be 0. So 0 plus 0 is 0, and hence we get the final, when the both inputs are 1, the output of the XOR gate is 0. This is also known as exclusive OR. Exclusive means only when one of the inputs are 1, then only the output is 1. So in OR gate, you remember, even if both inputs were 1, the output was 1. So this is not the case here. So only when only one of the inputs is 1, that's why it's called exclusive. Only when exactly one of the inputs is 1, then only the output is 1 for a 2 input XOR gate. There is one thing I should add. So we noted that what we talked about here is that when only one of the inputs in 2 input XOR gate is 1, then only the output is 1. What happens when there is 3 input XOR gate? So if there is 3 input XOR gate, again the output is 1. Output is 1 only when one input is 1. So please remember that. It is exclusive in that sense. So if some time comes, maybe I'll show you the truth table for 3 input XOR gate. But for now, I just wanted to point this out, that the odd number of inputs have to be 1. That's the idea. So here only one input is 1. So in that case, one input is 1 or 3 inputs are 1, then you will get an exclusive OR gate. Yeah, so let's move forward. Okay, so we do know that the expression for the output expression is AB bar plus A bar B. This is the expression that we know is true for XOR gate. The questions asked which does not represent. So you note option B first. It's very easy to see. The option B says AB bar plus A bar B. Plus 1. AB bar plus A bar B. This is the expression that we know is true for XOR gate. The questions asked which does not represent. So you note option B first. It's very easy to see. The option B says AB bar plus A bar B. So this is exactly what we saw as the XOR gate. So option B cannot be the correct answer because this is the expression for XOR gate. Note that we are to find which does not represent. Okay. Now for other three we have to solve it. So let's first solve the option A. So option A says A plus B times AB whole bar. Now, based on De Morgan's law says that AB whole bar is nothing but A bar plus B bar. So let's put that here. So we get A plus B times AB whole bar will become A bar plus B bar. And now we multiply. So there are two terms here, two terms here. So it will come AA bar plus BA bar plus AB bar plus BB bar. Now note that this term and this term will be 0. Why it will be 0? Because let's assume that the value of A is 1. Okay. So the value of A is 1. So 1 times 1 bar. So this will come out to be 0 when A is 1. Similarly, when A is 0, this will be 0 times 0 bar, which is again 0. So whatever be the value of A, the output is always 0. So this term will always be 0. Similarly, this term will again always be 0. So what I get is I get BA bar plus AB bar. I'll just bring the first term forward. So AB bar, and these are multiplied. So A times B is nothing, X times Y is nothing but Y times X. So I'll write as A bar P. Now note that this is nothing but expression of XOR. So option A is also the expression for XOR. So this is also XOR. So this option cannot be correct again. Now let's try to option solve B. We have already seen that it's XOR. So let's try to solve option C. C is A plus B times A bar plus B bar. Now note that we already solved this. A times B into A bar plus B bar. So option A and option C are effectively the same. So I'll just write it just for the sake of completion. A bar plus AB bar plus B bar A plus BB bar. These two terms go to 0. The bar terms, sorry, not the bar terms. This term and this term will go to 0. We saw that, right? This is the reason here. And finally, so it will come AB bar plus B bar A, which is nothing but XOR again. So but we see that yet again that option C is also XOR. So C cannot be the correct option again. Now let's come to option D. So option D says the output is, let's say the output is Y. Y is equal to A plus B times AB. I'll simply multiply them. So it will be A times AB plus B times AB. This will be, so A times A is nothing but A. So I can write this at AB plus, again, take B to the right side because it's commutative. So we can do that. Multiplication is commutative in Boolean algebra. So B will take that side. So it will be again AB. And AB plus AB is nothing but AB again. Because if you add 0 to 0, the answer would be 0. If you add 1 to 1, the answer would be 1 again. So this is part of Boolean algebra. So if we add the same signal twice, we get the signal again. Note that this is not the expression for an XOR gate. This is an AND gate. You know that the expression for AND gate is this. For a 2-input AND gate, the expression is A times B. So this is not, this is AND gate, right? We obtain AND gate here. So this is nothing but AND. So option A, option B, option C were all XOR. Option D is AND. So this is the correct option. Note that we are required to find which does not represent XOR. Option D represent AND gate. Option D does not represent XOR gate. And hence option D is the correct answer. Okay. Any comments you people have about this?
No, sir.
Okay. I just need to point out one thing because it is very important, I think, in this question. So what we saw here was that we saw so what's it? So I'll write the truth table for a 2 input XOR gate. Okay. So this is A XOR B. This is the symbol for XOR. So it is I'll write the inputs first, and we saw that the outputs would be 0 1 1 0. Similarly, if I write, because this is a favorite question for the examiners, 3 input gates. In the recent exams, if you see, they have asked 3 input gates, so I should cover that. So this is the symbol for 3 input XOR gate. You see A XOR B XOR C. So let's write the truth table for this. So I'm writing all possible combinations that are there for the 3 inputs. Pardon my writing. I'll try to compensate when I explain. Right. So the trick to remember is that the output would be 1 when when number of inputs 1 are 1. So the output would be 1 when one of the inputs are 1 or 3 inputs are 1. So there number of inputs 1 are 0. So the answer would be 0 here, because high inputs are even. Now see here, number of inputs which are high, so only C is high, A is 0, B is 0. So the number of inputs that are high is 1. Hence this will be true. Similarly, the number of inputs that are high in this expression are 1. Only one input is high. So again it would be 1. Here if you see, the number of inputs that are high are 2. 2 inputs are high in fourth row. 1 second. Yeah, so 2 inputs are high in the fourth row. So this will be 0 because high inputs are even. There are 2 inputs that are high, B and C. Similarly, if you come to fifth row, the number of inputs that are high is 1. Only one input is high. Hence the answer would be high. Answer would be 1. Here in sixth row, 2 inputs are high. So answer would be 0. The reasoning remains the same, because the number of inputs that are high are 2. They are even. Similarly, in the seventh row, 2 inputs are high. The answer would be 0. In the eighth is a very interesting case. This is why I wanted to draw this truth table. So the number of inputs that are high, the number of inputs that are high in this row are 3. So the answer would be 1. Why? Because high inputs are odd. To be more precise, number of high inputs. So please remember, this is a trick to remember. So you might not always memorize the truth table. So the trick to remember is that in any exclusive OR gate, the output of exclusive OR is high as long as the number of inputs that are high are odd. This is, remember just this, and you will be fine. You will be fine. Okay. Okay. So let us go to the next question, which is this. All right. The screen is visible?
Yes, sir.
Okay. I'll go ahead now. The problem statement from GATE Physics 2018 reads as follows. The logic expression which has been written here can be simplified to, the 4 options are A XOR C, option B A and C bar, option C 0, option D 1. So essentially we have to solve the logical expression which has been written here, and we need to simplify it to the lowest possible, easiest terms. So we'll do that. First, let's have a look at the truth table for some logic gates. So we just went through these the truth tables, what they represent in the previous questions. So for the interest of time, if you have any doubts, please stop me. For instance, if you have any doubts regarding the truth table for XOR or no, just stop me. Otherwise, I'm going to skip this because we have gone through it many times now. So I'm going to skip this and I will directly go to the question now. And you will populate the output column. That's all. In this question, we were given that this is the expression, and let's say we are required to find the value of this expression, the simplified expression, and I've assumed that the output is y. Okay, so now what I'll do is that let's just have a look at the first two terms here. So in the first two terms, what I'll do, I'll take a bar c as common from the first two terms. See, a bar and c both are common, so I'll get b plus b bar. So this is the result for the first two terms. Similarly, from the last two terms, I can take AC bar as common. Note, AC bar is common in the last two terms. So I take AC bar common, and what's left is B plus B bar. That's all that's left. Now, from these two terms, I take B plus B bar as common. Note that B plus B bar is common to both. And what would be left with? A bar C plus AC bar. Correct? Now, let's first evaluate what this term comes out to be. B plus B bar. Okay. So let's just. Can anyone tell me what B plus B bar come out to be?
1.
And in any scenario, can it come out to be not 1?
No.
Yes, there is. If B is X, remember there are three, we have always talked about that there are two inputs only, right? I've always said the inputs are 0 and 1. But actually if the input is neither 0 nor 1, that's why we call it input as X. So this is very rare scenario. When we do Karnaugh maps, K maps which we call, then we encounter this entity, this unknown quantity, or it can be anything, 0 or 1. Usually if nothing is said in your question, right, you just assume that it's either 0 or 1. It cannot be both. So you are correct. So B plus, we'll see that why B plus B bar will come out to be 1. But it's not always true. Remember that. In most of the questions, it will be true. So again, if nothing is said in the question, we'll assume that B plus B bar is 1. Just be cautious, because sometimes now the problems are getting a little bit, so the easier problems in exams like GATE and NET are getting over very fast. So the examiners are trying to put a little bit tricky questions. So just be cautious about it. That's all. If your concepts are clear, you'll be fine with that, I'm sure. I'll now just resume playing the video. Assume that x is equal to b plus b bar, and let's try to find the value of x. So I'll do the same thing. The input is b and x is nothing but b plus b bar. Correct? So what I'll do here is that, so this is b. Okay, let's try to find this. Let's try to populate this truth table. So there are only two possible combinations. Either b is 0 or b is 1. So if b is 0, b bar would be 1, and if b is 1, b bar is 0. Correct? Now let's try to evaluate the value of x here. X is nothing but b plus b bar. So it will be 0 plus 1, which will turn out to be 1. 0 plus 1, we know in Boolean algebra, it's 1. In the second row, we see x equal to b plus b bar. So the value of b is 1. The value of b bar is 0. So 1 plus 0, it will again turn out to be 1. Now, this is an interesting case. Whatever is the value of b, note that b can only have two values, 0 or 1. So whatever is the value of b, the output x is always 1. So this is always true. X is equal to 1 irrespective of the input. So I can write x equal to b plus b bar equal to 1. It's independent of the input. It's always true. Hence, now if I come back to my original expression, what I have obtained is b plus b bar equal to 1. Note this. Let's put this value here. So I'll get y equal to 1 times, note that the value of b plus b bar is 1 now. So that will be a bar c plus ac bar. So we'll get a bar c plus AC bar. Now note that this is nothing but the algebraic expression for an XOR gate, 2 input XOR gate with inputs A and C. So we see that. So I told you the XOR is nothing but A B bar plus A bar B. Here one of the inputs is C. Instead of B, it's C. So A bar C plus AC bar. So what we get is an XOR gate. right? So this was the question, and we simplified it, and we obtained that this logical expression can be simply written as A XOR C. Option A is the correct answer. Right. Next question. Now, any doubts, any comments regarding this question?
No, sir.
Okay, I try to point out. Just please stop me if anything is going too fast. Usually, what I do is that I try to be as slow as possible, even either that's in the class or in the videos that I am presenting. Okay. Gopal, you have a doubt? Gopal?
No, sir.
Okay, your
No.
hand was raised. Okay, it's fine. That happens. ठीक है. Just 1 second. Okay, so I'm going to we'll now move to the next question. Okay, 1 second, let me share my screen again. I hope it's visible.
Yeah.
Okay, so let's do this. The problem from GATE Physics 2019 reads as follows. Consider the following Boolean expression. The problem from... Are you guys also seeing double screen, or is it just me?
No, sir.
What's written on your screen?
Yes, yes, sir. There is two screen. Problem 2019 and 2018.
Okay. Now it's fine, right?
Sir.
Okay. The following Boolean expression. A bar plus B bar times A into B plus C whole bar plus A times B bar plus C bar. The question says it can be represented by a single 3-input logic gate. Identify the gate. The options are AND, OR, XOR, or NAND. This is a multiple choice question with one correct answer, and we need to find the correct one. Now let's look at the question carefully once more. So it's saying that this Boolean expression, let me assume this is Y. So this whole Boolean expression can be represented by a single gate. So this means this can be simplified to just one single expression, which contains and which is and which in turn can be represented by just one single 3-input logic gate. This implies that this, if it's AND, it will come out to be ABC. If it's OR, it come out to be A plus B plus C. This whole expression will simplify to either of these. If it's XOR, it will come out to be A XOR B XOR C. And if it's NAND, it will come out to be A, B, C whole bar. So we first will simplify this expression, and we'll try to find out which one of the following it matches. Now, I should point out that usually this is a difficult question, because in GATE in the earlier years, 4-5 years back, so the 3-input questions were not that common. So this is a 2019 paper. So in the recent, that's why I was saying the easier questions have just, I mean, they have been exhausted, but still this, if you follow the same logic that we have discussed till now, you'll solve this, and you'll see I'll not do any fancy things, just I'll try to do the things we have talked about till now. So this is the expression that we were given, and we'll just try to simplify it for now. Okay, so let me write it as, now what I'll do is that I'll take the first term as it is and apply De Morgan's law in the inner bracket. So we know that De Morgan's law is AB, okay, or I should say XY whole bar equal to X bar plus Y bar. So let's implement this on this inner square bracket. So what we'll get is, so X is A here. So this is, let's say, X, and this is Y. So what we'll get is, we know XY whole bar is X bar plus Y bar. So I'll get A bar plus B plus C whole bar. So let's copy this term, the second term. Again, this term will remain the same. And now I can now apply second De Morgan's law, which is X plus Y whole bar is equal to x bar times y bar. So I'll assume that this b plus c whole bar, look at it, it's the form of x plus y whole bar. So I can write it as simply b bar c bar plus a times b bar plus c bar. Now let's multiply the terms. So I'll get a bar times a bar. So I'm writing that a bar plus a bar, then b bar times a bar plus a bar b bar c bar plus b bar times b bar c bar plus a b bar plus a c bar. Now note this first term, a bar dot a bar. In Boolean algebra, x dot x is equal to x, because if 0 into 0 will come out to be 0 and 1 into 1 will come out to be 1. Hence I can write a bar dot a bar equal to a bar plus, I'll just rearrange these terms, so just for the sake of simplicity, plus a bar b bar c bar. Again, b bar dot b bar will be, using this expression I can write b bar dot b bar will be nothing but b bar dot c bar for this term c bar plus a b bar plus a c bar. Now let's have a look at this expression. Note that, just take, so I'll bring this term here first. Okay, so I'll write a bar plus a bar b bar c bar. So I've just brought this term here plus, again let me just combine this term and this term. Okay, so I'll write a bar b bar plus a b bar, second bracket, plus these terms remain the same, b bar c bar plus a c bar, right? Now I can take a bar common from these terms, right? It will be 1 plus b bar c bar. Similarly, I can take b bar common from this. It will be a bar plus a plus b bar c bar plus a c bar. Now 1 plus anything would always be 1. So even if this term is 0 or 1, it's irrelevant, because 1 plus 0 is also 1 and 1 plus 1 is also 1. So I can neglect this second term. So this will come out to be a bar times 1 plus b bar. Now a bar plus a. So let's say a bar plus a is nothing but 1. Because let's take the case when a is equal to 0. So when a is 0, it will be 0 bar plus 0, which is equal to 1 plus 0, which is equal to 1. Or when a is 1, so it will be 1 bar plus 1, 0 plus 1, which is again equal to 1. So a bar plus a will always be equal to 1. So I'll write b bar dot 1, this term, plus b bar c bar plus a c bar. Anything into 1 will be 1. So it will be a bar plus b bar c bar plus a c bar. Now look at these two terms. I can take b bar common again. So it will be a bar plus b bar into 1 plus c bar plus a c bar. Now this will come a bar plus, again 1 plus something is nothing but is 1 itself. So a plus b bar plus a c bar. Note that in the previous slide we had obtained this expression. We simplified y to up to this level. Now let's simplify it even further. Let me just take b bar as the first term, and I'll write a bar plus a c bar. Now according to distributive law in Boolean algebra, you can write as x plus yz is equal to x plus y times x plus z. So now let's just take this term, and let's say a bar is x, a is y, and c bar is z. So I can apply this distributive law over this square bracket. So my expression y will come out to be b plus square brackets, it says x plus y. So what is the value of x? It's a bar plus y. The value of y is a times x plus z. So what is x? X is a bar plus z. What is z? Z is c bar. Sorry, this is b bar. So it will be b bar plus, now a bar plus a, we have already noticed that it's 1. This will turn out to be a bar plus c bar. So 1 into a bar plus c bar is nothing but a bar plus c bar, and I can just rearrange the terms and write a bar plus B bar plus C bar. If we again apply De Morgan's theorem, it will come out to be A, B, C whole bar. Note that for two variables, the De Morgan's theorem is xy whole bar is x bar plus y bar. For three variables, it remains, the flow remains the same, x bar plus y bar plus z bar. Please note that this is important. For three variables, the De Morgan's theorem, the form remains the same. So this is an important thing that you should try to remember, so that you don't have to derive it in the exam itself. So our form was A bar plus B bar plus C bar, and if you compare with this, then we can write as ABC whole bar. Now this is what's happening here. We are adding the three inputs and then taking an inverter. This is nothing but a NAND gate, and hence the correct option is D, NAND. Okay, any doubts, any comments regarding this?
No, sir.
Okay, so is this mode better or the previous mode was better when I was solving the questions in the class itself? Which one do you find better?
This one.
Huh?
This one.
The videos, me presenting the videos and pausing them in between. That's the one you find better? Okay, ठीक है, I'll try to maintain this. Okay, so now I have we still have some time, so what I'll do, I'll solve one last question which I have. I don't have video for that because I didn't expect that we'll finish early. Are you able to see the screen?
Yes, sir.
Okay, so this is the question that is there from 2018 paper. In the figure, we have been shown a 2:1 multiplexer. Now we'll talk about what multiplexer is with this thing. This is a typical property of multiplexer. We'll just go through this, what it means, and we have been asked to find the correct implementation. So see, this is a multiplexer provides some functionality. How to implement this multiplexer is the question that is being asked. Now, what is a multiplexer? We should be very clear about it. So a multiplexer will have some n number of select or control lines. You'll see this word again, select or control. We'll see what this means. And if there are n number of select or control lines, there should be 2 to the power n. Sorry, it's not 2n, it's 2 to the power n. 2 to the power n input signals. And the most important property of multiplexer is exactly one of these 2 to the power n inputs will be sent to the output. Now, how will we select which one is selected? This will be selected by the signal. That's why the name select or control signal. So select or control signal will actually determine. So in this case, we have n equal to 1. We only have one control line. You see C stands for control. And since there is one control line, there can be 2 to the power 1, which is equal to 2 input signals. So we have 2 input signals, A0 and A1. Now, only one of these will be routed to the output. You see this. You can assume that it's like a switch. There is a switch in between. Now, which switch will close? That will be determined by C. So C will determine which of these switches will close. And please note that only one of these switches will close at a time. So both the switches cannot close. So the current, so to speak, you can assume so the current will be flowing only in one of these one of these paths. So either A0 will reach X or A1 will reach X. Both of them cannot reach X simultaneously. This is why the name multiplexer. So out of many inputs, only one input will be able to reach the output. And that's the whole game. And it is given that output X is A0. So when will A0 reach? The A0 will reach X when C is 0. This is written here. So when C is 0, this means this switch will become closed. This is just an illustration. There is no switch in between. I'm just saying for the sake of simplicity. However, if the value of C is 1, then this switch will remain open and this switch will close. So this is in the truth table terms, this is represented as this. So if controller select signal C is 0, the output X will be A0. If the controller select signal is 1, the output would be A1. So I have just put the table here, and this was the expression that was given. Now let's just look at the top row. Okay, what's happening there? So in the top row, when the control signal is 0, I told you this switch will become closed, and hence the value of X would be A0. So let's call this output for the time being x naught, where this denotes the value of C. So what will be the output? The output will be A naught. We know the output is A naught. And when is the output A naught? When C is 0. So this can be written as, because if you see, if C is 0, then only x naught will come out to be A naught. So we get the value of output as A naught times C bar. So this is nothing but an AND gate. This is multiplication. So A naught times C bar. So this is the A naught, first signal A naught, and this is C, and this circle denotes naught. So this is AND gate. So output x naught would be A naught times C bar, because C bar is the input to this AND gate. Similarly, if I now look at the bottom row, if the control or select signal is high, C is 1, I told you that this path will become open. So to speak, this switch has been closed, and thus, and let's assume that the output, actually it's x, but just for the sake of, I'm just breaking down for you, simplifying it. So let's say the output is x1. So what will be x1? X1 would be A1 times C. Why? Because only when C is equal to 1, then only this expression should be valid. So I can write x1 equal to A1 times C. Now this is nothing again but a NAND gate. So where the two inputs are C and A1, and the output is x1. Now comes the most important thing. I told you at any given point of time, either this will be true or this will be true. Both cannot be true at the same time. So what we have is an OR in between. So x, the value of x can either be x naught, this value, or it can be x1, this value. Hence x can be written as x naught plus x1. So this was x naught, this was x1, and I have drawn the circuit. See, I have replicated this circuit here. You see the green circuit is this one here, and the blue circuit is this one here. And what I am doing to get the final output x, I am doing nothing but x naught, and this is an OR gate, so it will do the summation of x naught and x1, and we'll get our final output x. So this is what's actually happening here. And so what we get, so just remember the form of the circuit. So this is A naught and A1 are not inverted, and we have two AND gates and one OR gate. So we have two AND gates. So this is the one. We have two AND gates and an OR gate, and when the A naught is the input, the C is inverted. So A is our correct option for this multiplexer. Multiplexers are actually very important in real life circuits, as well as for the sake of your examination. So and these are very straightforward ones. 2:1 multiplex is the simplest multiplexer that we can make, and you should try also some questions, some 4:1. 4:1 is slightly complex, but the concept remains the same. So you should try to solve them row by row, like I've solved it here. So if you go row by row, you can never go wrong. Each row will give an algebraic expression, and finally all the algebraic expressions can be simply added using an OR gate. So it's a very simple. Once you practice one or two questions, you'll realize that multiplexers are not difficult. Some people tend to skip them, but they are not at all difficult. These are very straightforward, very simple questions. So yeah, so that's it from me today. Yeah, so if you have any doubts, please go ahead and ask me. Any more doubts, I guess I should say. Anything?
Sir, I have question.
Yeah, please go ahead.
Sir, from previous class.
Okay.
You did last question gate 2019.
Let me share the screen so that all others can also see. Okay, just hold on. So last class, let me open the question. This question, right?
Question. Yeah.
This one? Rajiv?
Yeah, yes, sir.
This one?
Yeah.
Okay.
Sir, answer, what we get is x0 is equal to 0 and y is equal to 0.
Correct. That's the answer that we got. I think x is equal to 0 and y equal to 0 is the answer that we got. Yeah.
But answer key is 0 1.
That is wrong.
Okay.
Answer key is wrong. In fact, when is this? This is 2019 paper, kya?
Yeah.
So I wrote my gate in 2019. I challenged this answer key. I remember that. You can challenge the answer keys, right?
Yeah.
I challenge this answer key that this is a wrong answer. Although my challenge was not successful, but I will still say that my answer is correct. Yes. If time permits, we'll solve this again in the next class when we do sequential circuits. Next class, okay. Before I forget, next class we are doing sequential circuits, JK flip flops, counters, and stuff like that. So if time permits, I'll try to this question again. Okay, so that I can clearly establish that the answer is indeed x2 equal to 0, y2 equal to 0. Okay. Answer keys are wrong sometimes, so just don't worry. Just as long as your concepts are clear, you will be fine. That's it. Okay. Is it okay?
Yes, sir.
Okay, yeah. Any other doubts, people?
Sir, can you share PDF?
I do not have a PDF. That's the problem. Okay, what I'll try to do is no. See, in more than PDF, these videos will be uploaded. So for each question, right, we have a video. I just showed you 4 or 5 videos today, right? So what I'll do is that we are uploading the videos one by one on NPTEL portal. So I request you to go through them. You can watch in two times speed. So each video is like 7 to 8 minutes long. So every video will take like 3 or 4 minutes. Because PDF it will be difficult for me, because when I'm speaking, I'm saying something and I'm not always writing that. So that's the thing. That's why I request you to just go through the videos. We'll be uploading them. We have when is the next exam? If they are not uploading by the end of this month, I'll share the videos myself. Okay, just don't worry. I'll give you the videos. So just let me know. Let's say on 3 weeks later, around 23rd, 24th of October, just let me know if the videos are being shared or not, because we have been uploading videos, and NPTEL is doing they are checking that our videos are good quality and concepts are correct or not, and we'll soon start uploading them. If not, I'll share myself. Okay.
Okay, sir. Thank you.
Okay, yeah, thanks. Okay, thank you everyone, thank you
Good
for
night.
attending. Good night, bye bye.